Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Today is the last lecture, the final lecture, and so we are going to go a little bit through the material that we've seen during the semester, and after that I'll talk a little bit about the exam. I'll tell you about the course evaluation. Thank you very much for answering. I'll also tell you about the kind of feedback that we can use for future editions of the lecture. Then we'll play a quiz game, Eiskage 100, as we do every semester, and we'll see if you manage to win against the representatives of the TA team right here. All right, so let's proceed. So we've covered quite a lot during the semester, right? There's a lot of different topics. In fact, it's a lot of different ways of retrieving information, but there are links that we saw between them. It's not entirely disconnected. And so this is the basis for everything related to information retrieval. If you looked at the book, who actually read the chapters of the book throughout the semester? Some of you should for the exam, right? I recommend reading them. It's pretty much the same as the lecture, but with a different angle. That's a good way to strengthen your knowledge. But if you paid attention to the book, you will notice that half of the book is actually machine learning. And in fact, it's tightly connected to machine learning. But of course, I was careful not to touch that too much. But if you connect the two, you can imagine all the power that you get out of this. In the first lecture, I made a bit of a provocative statement because I told you that this is in fact a database lecture. Yes, exactly like the relational database systems lectures in the second years of computer science curricula. It is a database lecture. The reason I'm saying this is that there are 5 fundamental shapes of data out there. 5. There's tables, like relational tables. There are trees, which are denormalized tables. There are cubes that are even more normalized tables than the relational tables. There are graphs, which can have cycles. And finally, there is unstructured data, which is actually text, but by extension, it can also be images, videos, audio, and so on. And unstructured text, in fact, is a shape of data like any other. It means that you want to query it, to extract information from it, to look up information, to aggregate from it. So in fact, we need to do pretty much the same things. And you might have noticed that a lot of things that you learned in relational databases, they also apply to information retrieval. For example, in a relational database management system, you have indices. Right? You have hash indices, B+3 indices. We also have them in information retrieval. In a relational database management system, there is the notion of an input collection of rows that is a table. Well, in that case, it's a collection of lines of text or a collection of documents that we process. Then in a relational database management system, there is the notion of a query language, like SQL or SQL. Well, in information retrieval, there are also query languages, several of them, right? There's the Boolean query language, there is phrase search, and so on and so on. So there are also plenty of ways to design query languages for text. So this is just to really insist on the fact that this is really a data storage and management lecture, just focused on unstructured data. So we started at the beginning of the semester by making assumptions, because we always need to assume things. And in particular, we assume that the input consists of a set of documents. And in our first attempt, we assumed that the goal of a query was to select a subset of the documents. These are the ones that you return to the user. So at first, we did not try to rank the results in any way. It was only about retrieving the documents that match your queries. And we see here this proto-query language that is based on logic with and, or, and not. And you can issue your queries like that. And the predicates are actually words or terms that match documents that contain them, right? So this was our first attempt. We saw that the definition of documents is not that easy, right? At first, if you're in a library, of course, a document is a book. It's easy, right? But in general, as soon as you generalize and you have other kinds of supports, in particular digital media, like what you have on the internet, web pages, files, it's no longer that simple, right? So one of the messages in this lecture is that you always need to think about what you are doing, find the right granularity, right? So we have this concept of documents. We have this concept of term, that is just another term for a word. We also saw that characterizing what a term is also not so easy, right? The very naive way to proceed is to just tokenize by spaces, and everything that is in between spaces or punctuation is a term. But then we saw that it's not so easy because ETH Zurich is a term, and yet there is a space in the middle. Same for Unterwalden, Nittenwald. So terms are not so easy to define, but yet we need this level of abstraction in the same way that in the relational database systems, we have the notion of tables that have columns and rows, attributes, and so on. The concept of a relation. Here we need the concept of documents, the concept of term, and the concept of relationship between documents and terms. Right. So this relationship between documents and terms, we saw that it can have multiple facets. The first one is to see a document as a set of words, meaning that you ignore the order of the words and you ignore the number of times that they appear in documents, which is equivalent to vectors of Booleans, representing a document as a vector of Booleans. Of course, when you do this, this assumes an order in the terms, right? But this order is arbitrary. This is just the coordinate system of the vector of Booleans. Then you have the concept of what others besides sets of words. What do we have? Anybody? This is what we saw during the semester, right? Anybody? Sets of words, yes. Bags of words, yes, and lists of words, exactly. So we have sets, we have bags, and we have lists. The bags throw in the number of occurrences in the documents, that the number of times the term appears, and the list also takes the order into account, right? So then we saw that if we consider vectors of Booleans, we can represent the entire collection as a matrix, where every column is basically a document. It's a vector of Booleans, and then you get a matrix if you consider all documents, right? So this is called the incidence matrix. We saw it's extremely inefficient because there's a lot of zeros, so it's very sparse, so that's not a good way to store it. And instead, we use this different representation, which is not sparse, because here you just store what you actually need. And it consists of terms on the left that are connected to posting lists that are just lists of document IDs that contain them. And we saw that these purple cells, now we know how they are called. They are called document frequencies, right? It's the number of the length, the size of the list, basically, that comes after it, right? Then we saw that if you want to execute a Boolean query, you need to go through the posting list. And for example, if you want to execute an AND query, you need to intersect the two posting lists, go through them. And we saw that this can be done in linear time, right? Then we saw that the construction of the index also is not trivial. We saw that this is highly language dependent, how you would do this. In some languages, you would use stemming. In some other languages, you would use lemmatization, as we saw. So all of that is a huge set of decisions that you need to make when you build your system. But we saw that you can evaluate the system. So if it doesn't evaluate well, you can just revisit this and change the decisions and rebuild a new system, right? Hoping that it will perform better. All right. So we collect the documents, we tokenize, we do some linguistic preprocessing, and then we build the index finally. We saw that when we do this, there is something that we like to do a lot in these systems, is that instead of considering the original way that the terms appear in the original documents, these would be called tokens. when you have an actual physical set of characters corresponding to a word in the document. It's called a token, a positional token, to be even more precise. But what you do is that typically you group these tokens in equivalence classes. When the words look alike, uppercase, lowercase, or even the different conjugations of the same verb, like be, is, are, and so on. So we do these sort of things, and this is what we call a type. The name for that is a type. And so what we do typically is that we use the terminology token for what you have in the input documents. The terminology of type is when you do your equivalence classes, and the terminology of term is what you call what there is on the left here. When you have that's called the vocabulary, the set of terms. Okay. All right. We saw that you can have stop words, so you can throw away those that appear frequently, even though that practice actually has diminished over time because now we have enough power to also process them. We also saw you can use query expansion in order to have an asymmetric version of the types, right? So the types that would be symmetric, an equivalence relation is symmetric, as you learned in discrete math. But there is an asymmetric version where you can expand the index or you can expand the query by throwing in more terms that are equivalent to the first one. But it's asymmetric because in that case, that wouldn't be an equivalence relation. There is a relation, but it might not be an equivalence relation. Okay. Then we saw that you can use these magical, very mechanical and algorithmic stemmers that automatically group the words in equivalence classes. So this is the Porter stemmer, which is probably the most famous one. And all the words that end up in the same stem after applying this algorithm would form a type and would be together as a single term in the index. All right, then we saw a few optimizations, right? You can have these skip pointers in these postings lists, which allow you to jump directly for the very long list to a bit later. So you don't have to traverse one by one. You can take the pointer and the shortcuts and travel all the way to the other side. It's like in Harry Potter with the fireplace, right? You just immediately transport yourself all the way to the other side. Okay. Then if you consider different kinds of languages, like not the Boolean query language, but phrases, which is typically what we do when we use a search engine like Google or Bing. And when you do that, you quickly notice that having sets of word semantics is not very nice because that doesn't capture the order of the word, so you cannot really do any phrase search. So you need to extend a bit the index into what is now here called a by-word index, meaning that instead of indexing term by term, you index pairs of terms that are consecutive in the input documents. So you get something like that, and that allows you to do phrase search. The alternative, which is a different way of extending the standard inverted index, is that you keep track of the positions. So then you have the list of words, semantics, and that every posting also contains the positions at which a term appears. So you also know the number of times it appears and the position. And with this, you have enough information to actually execute a phrase search, because all you need to know is that these are consecutive integers, the positions of the words you're looking for, right? We saw a difference between these two approaches is that this has full information. You will not get any false positives, right? You might get false positives because of equivalence classes and types, right? But you might get false positive with this one, because in that case, you might have, I showed you a few examples where you might return documents that do not actually have the sequence of words as in the query, even after the equivalence classes, right? So these are the two ways. And this is a reminder that the index is called the standard inverted index. And the reason it's called standard inverted index, this one is called the standard inverted index, is precisely because it gets extended into non-standard inverted indices, like this one and this one, right? So this is really a basis on top of which we can build more indices. Now in this standard inverted index that I showed you, I told you there is this vocabulary, which is just a set of the terms that you have. But this set of terms, the vocabulary, is actually organized in a data structure, that facilitates looking at the terms. This data structure is called a dictionary, right? It's a dictionary of terms. The reason it's called dictionary is pretty much because it's like when you do binary search in an actual paper dictionary, right? It's the same idea. And this data structure can typically be a hash table or B plus trees. And we saw, I mean, you know that this is general computer science knowledge, that for hash tables, if you don't have too many collisions, it's instant. The lookup is instant. And for B plus tree, the lookup is, yes? Logarithmic, exactly. You have logarithmic lookup. But the B plus trees give you an advantage. They can also support range queries. So if you look between a word and another word, then it can be useful for spell checks and wildcard queries. All right, very good. So hash tables and B plus trees. A B plus tree looks like this. I warned you, it's not fully standardized. People define B plus trees in different ways. If you look at different textbooks, if you look at the Wikipedia page and so on, there's a lot of conventions. So in order to isolate you from all of that, I gave you one convention, which is the D+1, 2D+1 convention. I warn you that the number of children is not the same as the number of keys in a node, because you have one more child. If you have, for example, in that case, 3 is merely, that's 3 keys, but there's 4 children, right? It's just the interval thing. So you always need to be careful. If the number of children is between 3 and 5, then the number of keys on a node is between 2 and 4. You need to remove one. Okay, well, so the root is an exception, and it's fine if it only has 2 children. So the lower bound doesn't apply to the root. Okay, then we looked at wildcard queries, which contain these asterisks in the middle. So you might have multiple wildcards also in the same query. Of course, we started with the easy ones, right? So the easy one is when you have a wildcard at the end, and then we saw it's just a prefix search in the B plus tree. So if you have a hash table, of course, that will not work. You cannot process this. But if you have a B plus tree, then you can easily process a wildcard query if the wildcard is at the end. And in the case that the wildcard is not at the end, but in the middle, then we had a new trick that is called the permuterm index, where you compute all the rotations of every word, and that is how you actually manage to process wildcards when they are not at the end of the query, right? Then we looked into so-called k-grams. K-grams is the same thing as k-words. K-words is just sequences of words. In that case, it's sequences of characters within a word, right? So when you say k-gram, this is what it means. So we saw 1 gram, 2 gram, 3 gram, 4 gram, and so on and so on, right? So this is the idea, and typically we use that also for spell check with 2 grams, 3 grams, 4 grams that allow you to, when a word is misspelled, you can still rely on some of the characters inside to locate the most likely candidate. Note that the notion of grams, in that case, in the context of spell check, we used it for characters, sequences of characters. But in the context of language models or Markov chains, it might be that you see the word gram, like unigram, bigram, used with words. So you need a bit of flexibility here to just be aware of that, right? Remember, in language models, the unigram model, we meant here words, not characters. Okay, but it's always clear from the context. Then another tool for spell checking is the edit distance, so-called Levenstein distance. We saw the super powerful dynamic programming approach. When you have an exponential search space that would be intractable to use, then you can actually quotient the search space in such a way that it becomes polynomial, which is the perspective I gave you on dynamic programming. And then you can just fill in polynomial time this table in order to determine the distance. And with these pointers, you can even retrieve the exact sequence of edits between the two words. Then there was yet another tool in our toolbox called the Jacquard coefficient. This also estimates how close two words are, but it's not a distance. We saw why. It's just a coefficient. It's actually large if the words are close, and small if the words are far away from each other. And the Jacquard coefficient is just a quotient. It's a division. You look at the k grams for some value of k, like in that case, the trigrams. and you compute the cardinality of the intersection divided by the cardinality of the union, and that will give you how close the worlds are. So 1 means they have exactly the same k-grams. They might still not be the same worlds, but at least they have exactly the same k-grams. And 0 means they have absolutely nothing in common, right? So this is also a way to quantify how close two worlds are. And by the way, you saw that like this and many other places, there is not only one way to do things, right? It's a whole history over multiple decades of people who contributed ways to do things. And so there are often several ways to do the same thing, right? So edit distance, Jaccard coefficient. The Sandex algorithm is also used for spell checking, and this is based on how things sound. Careful, this is specific to English. In that case, if you use it on a different language, you might want to do something different. But I gave you the algorithm, and you can basically convert every word to some sort of fingerprint of how it sounds. And then you get, again, types. You can group them in equivalence classes, and all the terms that sound alike according to the Sandex algorithm would be in the same equivalence class. Okay. Then we started looking still into optimization, but physical optimization. And we saw that it's very important in order to do these things to understand what's happening at the physical level. We saw that in order to store, for example, you can store in the cache of the CPU, in the working memory, on disk, on tapes, and there is even an intermediate level between memory and disk that I never remember the name of, but I think you know, right? This thing intermediate between working memory and disk. Yes, this one. Can you repeat? Non-volatile? Memory, exactly, yeah. So there is even a new one in the middle that is quite popular in databases that kind of has benefits from both sides. So I could even now redraw that slide with 5 levels instead of 4. But what I wanted to distinguish here is the speed, that it's faster for the upper levels, but it has less capacity. And some of them disappear if you have no electricity, and some of them stay if you have electricity. So that also plays a role, right? So if you want to store the collection and index, it has to be on a persistent memory like the disk. And if you want to be fast, like when you process the queries, you do want to copy it over to volatile memory because it's faster. And yeah, there's also a cost thing, right? It's very cheap if you have tapes, very expensive per byte if you have the CPU cache. All right, that's pretty much all I know because I'm not a hardware person, so I don't know much about hardware. But this is usually sufficient to understand what is going on. Abhishek is an expert on hardware and coherence protocols. All right. So when we optimize, we also saw that if we build the index, we saw that the posting is a pair term document, right? Even though there's only the idea of the document is in the inverted index, it's still a pair because the term is implicit from the left, right? So we need these pairs. But the problem is that if you build the index and you have the pairs that flow around in memory, if every time you write the entire term, if it's a long word, then you're going to waste a lot of memory because you might have the same term appearing plenty of times. So this is a compression scheme where you replace terms with term IDs. I think it's also known as a dictionary encoding because you can also do that in relational databases if you want to compress the storage of a column where you often have the same terms. All right, so it's a compression technique, and it is used in particular for what I would call the first generation algorithms to build indices, where you process the collection in batches. So you cut it into batches, for example, 1 million documents, and then 1 million documents, and then 1 million documents. That allows you to build the index if it wouldn't fit fully in memory with all these pairs. So you do it in batches, and for every batch, you build all the pairs, put them back to disk, then go to the next batch and so on. And at the end, you merge everything into the final index. So that's called BSBI, blocked search-based indexing. Then comes what I would call the second generation indexing with a few improvements over the first one. And one of the improvements was that we get rid of the term ID, the term ID encoding. just because we found a better way here, which is that you directly build partial inverted indices. So for every batch, you build the partial standard inverted index, store it back to disk, and then you merge the standard inverted indices. And merging the standard inverted indices takes linear time, right? So we love linear time at large scales. This is what works best. All right, so single pass in-memory indexing. This is really, again, these two are when the data might not fit in working memory, so you need to do it batch by batch. And finally, there is the super powerful MapReduce paradigm that allows you to process the data if it doesn't even fit on your laptop. So even the collection doesn't fit on a machine. That's what you would do with the entire internet, for example. And that's typically, I mean, of course, I'm oversimplifying, right? But this is pretty much how Google or Bing is implemented. This is basically a round of MapReduce over the entire internet that is repeated every 48 hours. Right. It's an oversimplification. Of course, it's more complicated than that, but in essence, this is how you build a search engine like Google. Okay, so it's no coincidence that it was actually invented by Google, the MapReduce. All right. Then we saw that in some cases, your collection, especially if you're indexing the internet, might actually be alive. You keep getting new books incoming, they are modified and so on. So then you have a new problem because you need to update your index. So we saw a few strategies, but one of the most important and influential techniques in this is called this log structured merge tree, where you have this idea of flushing every time you've completed a batch, you flush it, and then you keep flushing new batches, but as soon as you have several indices of the same size, then you merge them into a larger index. It's like fossilizing, right? So the more you go to the right, the more you have the ancient fossils of what was there for long, and you have the fresh ones that would be on the left. But what's important here is that every time, for every query, you still need to look everywhere, right? But this technique minimizes the number of times you merge two indices, so it's very efficient. This is a technique that is also used in white column stores in big data in order to store on HDFS. So, but this is a different story. So LSM trees, log structured merge trees. All right. Then we saw a few statistical laws which are useful for further optimizing the size that an index takes. We first ask ourselves, if I keep adding new books and new books and new books in the collection, how does the number of unique terms evolve? And here we had a surprise, because spontaneously, anybody would think the number of terms in a language is limited, so that should be a hyperbolic curve that at some point has a horizontal asymptote, and then it doesn't increase anymore. But surprise, surprise, that's not what happens. This is just experimental. It's not a theoretical thing. It's actual data analysis shows that it's actually more like in the square root of the number of documents, right? So the square root, and so the value of the constant in front of the square root is typically between 30 and 100, but that might actually vary between languages and depending on the field as well. A comment here, it doesn't matter if here on the x-axis I have the number of tokens or the number of documents, right? Because it's just, they vary by a constant, which is the average number of tokens per document, right? So you have the two versions, either it's in the square root of the number of documents or in the square root of the number of positional tokens. Okay, and we have the twin law, which is the Zipf's law. So there's two of them. Zipf's law is the number of terms depending on the number of documents. And Zipf's law is when you rank the term frequencies. And sorry, not the yes, the term frequency. So the number of times that terms actually appear. And it turns out that you get here some 1/x curve, right? So the frequency decreases like that. So the most frequent terms they appear very often, and then for the second one, 1/3 for the third one, 1/4 for the fourth one, and so on and so on. So this is how they tend to distribute. This graph, actually, I did it. I think I downloaded Wikipedia or something, and then executed the calculations, and this is what you get out of it. All right. That's Zipf's law. Then you have compression techniques on the dictionary side, which allow you to take less space to store your dictionary of terms. And this is one way. There are several ways of doing that, but one of the popular techniques is to have this very long string with the terms, except that the string is a bit shortened, because when you have common prefixes, for example, you don't repeat the prefixes. And another optimization is that you have a pointer to that list only every k terms, right? And then you have these intermediate integers that tell you the separation between them. All right. So this allows you to compress things a little bit. This one is called front coding. So you can compress the dictionary, or you can compress the postings lists, which is, I find it even more exciting. So how do you compress postings lists? Well, you can use variable byte encoding instead of a fixed encoding, for example. That takes up roughly 50% of less space. But there is something even better, that is the gamma encoding, which seems inefficient at first, because it seems like it doubles the number of bits that you need. But actually, for the very small integers, it squeezes them so much, like a single bit to encode one, for example, that it's actually efficient. So this factor 2 here, it's actually the constant roughly compared to the entropy. So I explained to you that a universal encoding means that it is optimal asymptotically for any distribution in the input. And we saw that for the gamma encoding, the absolute upper bound is 3. So the average length of this encoding is at most 3 times at most 3 times the entropy. But in practice, it's closer to 2. So 3 is the upper bound, but you see here it's not exactly 2, it's slightly higher than 2, right? So 3 is very conservative, but it feels like a 2, like a constant factor of 2. So if you are ready to pay that cost of the factor of 2, then in fact, overall, you get something that's regardless of how the document IDs distribute in the posting list, it's going to be efficient on average. A reminder also that since document IDs are increasing in the posting list, we don't actually encode the document IDs, we encode the gaps, right? This is also one of the ways of getting smaller integers. All right, then we moved on to ranked retrieval, where instead of just outputting subsets, we output ranked lists of documents. So we needed a technique to score. So a basic technique would be based on this some sort of formula. So this is what you used to have in libraries maybe 30 or 40 years ago. You would go to a library and have systems like this that would use traditional relational database indices on top of the posting list. And so this is how you would retrieve your data. That allows you to score, actually, depending on where the query is successful. But a more modern technique called the vector space model is based on the use of TF-IDFs, for term frequency times inverted document frequency. This uses the bag of words model, meaning that you don't care about the order of the words, but you care about how many times they occur, which is the term frequency. We multiply them with the IDF, the inverted document frequency. That's the logarithm of n, the number of documents, divided by the document frequency. And the TF-IDF, given a word in a document, gives us the weights that we then squeeze in a vector. When we squeeze them in vectors, so this is what we get as bag of words, vectors of numbers with the TF-IDFs in there. And then some magic happens, because then it's a beautiful world of linear algebra where every document can be seen as a point in there, in the first quadrant, because it's always positive. And so a query as well. Query can be put in there, and then it all comes down to looking at the angle between the query and the documents, right? So this is really extremely powerful. It's so powerful that even in machine learning, it's used all over the place. That gives us a good model to score. So the higher the angle, the lower the score, and the smaller the angle, the higher the score. It's basically the cosine of the angle, the score. All right, so this is what you get. And we saw also that it does need to be TF-IDFs. You can, if you don't like TF-IDFs, you can change it to something else. You saw that there is a restaurant menu called Smart, and that allows you to tweak things and change if you're not happy with TF-IDFs, right? So again, the inner product or dot product as a score, which is the cosine of the angle, so to say. All right, and so once we have established this as the score, we saw that computing the scalar product, in fact, amounts to summing these things over all documents and all terms by accumulating them in buckets, one bucket for every document, and we sum over the terms. We saw that we can either traverse that document first or term first. So either you do document by document and then for every document all the terms, or you go term by term and then you do all the documents that are in there, right? This is called evidence accumulation. You accumulate evidence that documents might be good answers to your query, right? Okay, that's the smart notation. It's the restaurant menu that allows you to pick. Then we moved on to what I told you is the master's level with probabilistic information retrieval, which is yet another way of doing information retrieval. And here the paradigm is to sort the documents by probability of relevance to the query. The higher the probability of relevance, the higher the score, and the lower the probability of relevance, the lower the score, right? So here we sort them by this probability of relevance. However, we saw that computing that directly is just impossible. It's like computing the probability that it's raining outside. So what we do is we use this magic trick of the base formula and swap around the sides. And it turns out that then it becomes easier if you throw in a lot of simplifying assumptions, which we had to do. And then, surprise, surprise, we arrived to something that is the sum of the log of n over dt, which gives us the justification for having the IDFs in the evidence accumulation, right? Okay, and you see that because we have this fits with the evidence accumulation, right? You can also use this technique using these weights instead. Okay. Finally, at the master's level, we looked into language models, which is reminiscent now of ChatGPT, but it's the first year that I'm saying that because it didn't exist last year, or at least it wasn't hype last year. It's the idea of actually generating text, like generative algorithms. And we saw that you can basically just toss coins at every step. You decide, do I stop, do I not stop? Or you decide on the next word by flipping a coin every time. And we saw that with the chain rule, this is what you get, right? So the probability that you get D1, D2, D3, D4 is the probability that you don't stop times the probability that you get D1 times the probability you don't stop times the probability you get D2, knowing D1, times the probability you don't stop times the probability you get D3, knowing D1 and D2, times the probability you don't stop times the probability you get D4, knowing D2 and D3. Assumption in there, I dropped D1. This is because of the Markov rule. In that case, with order 2, because we only remember the 2 previous words. And then P stop, that's actually stopping. So this gives you a probability distribution on what you generate. And so you get a ChatGPT-like output. And here you again had one of these crazy thought experiments that at first sight don't make any sense and sound completely crazy, but that actually give you a technique for an information retrieval system. And in that case, what we said is that in the thought experiment, we imagine that we use the documents, train them into language models, generate something randomly, and it turns out to be the query. And then we ask ourselves, what is the most likely documents that could have just by chance generated query Q? And surprise, surprise, here, again, just like probabilistic retrieval, we land it right on the term frequency, which then gives us the justification for also using term frequencies in the evidence accumulation, right? So now, if you look at evidence accumulation, you know why the TF is there, TFTD, that comes from language models. At least it's justified. Even if it was justified later, it's still justified by language model. And the IDF can be justified with probabilistic information retrieval. All right, so it all fits together, what we've seen. And then we saw that you can evaluate how good your system is with the precision and the recall, which are the two main ways of doing that. But there's also specificity. So we've covered all of that. Then you can do some cooking and merge them into some more complex measures. So this is an example that mixes precision and recall using some harmonic mean, like 1 over the average of 1 over. Then you can add weights if you favor precision and recall. This works for the systems that do not rank queries, but for the systems that rank queries, we saw that we need to go through the results one by one by one by one, and we just draw the curve of how the precision and the recall evolve, and then we get that kind of curve, and that tells us whether a system is good or not. And a good system will keep a high precision and not drop immediately. This is an okay-ish system. I mean, it drops quite quickly in precision. No, actually, it's an awful system, because this one looks almost random. So a good system would really be more like a curve that stays high and then gets low. Because I told you that the systems in that case, for example, the recall specificity curve, if you have a system that is not going up and right, but instead goes right and then up, that's also a good system because you just swap if it's positive or negative, right? So it's an awful system is really a system that is diagonal here. Here, so this I switched to here because here it's obvious. Here it's less obvious because even if you could technically swap what is positive and negative, if you have a search engine that returns the top 10 and then top 10, I'm not sure it's so easy in that case to do that swap between positive and negative results, right? Okay. So, quick words on the exam before we take the break. Everything we've seen in the course is exam materials. So the lecture slides are exam material. The book chapters that I ask you to read are also exam material, but they coincide with the lectures. The recordings are exam material. They're all on YouTube. The textbook, the theoretical exercises are exam material. The practical exercises, like the programming assignments that the TA team prepares, also, even though on exam day, you won't have to program, right? It's just answering Moodle questions. And the clicker questions are also exam material, but to take with a pinch of salt, because these questions are not designed as exam questions. They're only designed as discussion questions to trigger discussions. Okay, so the exam. I think it's August 25th. Is it August 25th? You received, right? I think it's August 25th. So this will be in a computer room, usually it's either the main building or on the ONA near Earlycon. You will get at most 60 questions. These are specific instructions that I gave to the TA team, no more than 60 questions. These are going to be Moodle questions, right? Just like for what you had during the semester, except that, again, these are going to be exam questions. So the level of precision is going to be much higher than in the quizzes during the semester, because during the semester, the goal was to push you to research a bit, right? So for the exam, it's even more precise. So 60 questions at most, no negative points. So you really should answer everything. You don't know, just pick an answer at random. Doesn't cost anything, you're not taking any risk. So no negative points. And we also try to give partial points whenever we can. So if you get in the same question a few right and a few others not right, then whenever we manage, we try to give partial points. So this is mostly how it works. The exam time is actually generous. Normally it's meant so that a few of you will be able to leave early. So you can leave early if you're done. Then after a while, like 15 minutes before the end, you can no longer leave and you have to stay, and then this is the end of the exam, right? If you need US keyboards, we should organize, so the TA team will organize a poll to ask who of you wants a US keyboard. You can have one, and then we'll make sure you do on exam day. In the worst case that you don't ask for one, if you don't look at your fingers when you type, you can actually still change it logically in the operating system. So you can still have a Swiss keyboard, but change the actual layout to US in the last minute, right? But still, it's good to tell us in advance if you need a US keyboard, so we can organize things. You should arrive between half an hour and the time of the exam, so half an hour in advance, because then you have plenty of time to arrive, to find your seat and so on, because that way we can start the exam on time. So everything is material, but I just want to make you less worried regarding the last sections like probabilistic information retrieval or language models. For the exam, in the case of these, we don't push it too much. So for example, for probabilistic information retrieval, there will not be something like these super complicated formulas you know that we had, but you might still get basic questions on the base formula or have to solve a problem like the whether it's raining outside given the umbrella. So that you might get at the exam. Or you might get theoretical questions, but we are not going to push the difficulty level to insane levels, right? For the language models, it's the same. You might get some questions such as we give you some model and the weights of the model with the conditional probabilities, and we ask you, okay, what's the probability of generating that sentence, right? And that would be something like this then. We might also ask them, so there's the k-gram models. We might also ask them for the unigram model, where you also have to account for the for this multinomial distribution. But again, we try to keep it reasonable, right? So we are aware that that this is in terms of difficulty, this goes higher, right? Okay, but we'll have some in the quiz that are related to this, so you get an idea. Okay, do you have any questions before we take the break on the exam? Anybody? Is it all clear? Okay. Who feels comfortable with the exam or confident, or okay, any of you? Who is a bit worried or nervous? Some of you too. I can understand that, right? But you have the summer to prepare. You have June, you have July, and you have a good part of August. You should register to element.it.ethg.ch, that's the chat server, so you can talk between each other. So I encourage you to explain to each other the material of the lecture. It's a great way to learn, to actually explain to other people. It's not a competition. You get grades, but there is no grading on the curve thing. That doesn't exist. So the more of you succeed, the happier I am. It's basically that easy. So you can really work together and help each other. Ask the TA team on the chat server, on the Moodle forum, and we will help as good as we can during the preparation. We'll release past exams as well, so they can see what they look like. I think the FIS has community solutions also on the server that you can look at, so you'll have a lot to practice. Okay, we'll take a break now, and we'll be back at quarter past, maybe 16 past, and then we'll continue with the quiz trial, also talk about the course evaluation. All right, so see you in a quarter of an hour.